project in state of Minnesota, which was really optimizing their water treatment plant and cleaning up their distribution network. A little bit of background about the Sabin Water Treatment Plant. It's a EPA demonstration site, which was built in 2006, and it was primarily designed to remove iron and arsenic through co-precipitation. The plant wasn't designed to remove moderate levels of manganese in the water, but the primary concern was arsenic levels. The standards were changing, and they had about 50 parts per billion of arsenic in their well water, so that was more the immediate concern with the water plant and not the secondary standards of manganese. The distribution network, over the past several years after the plant was built, the operators started seeing episodes of brown and black water, whether it was flushing the hydrants or through the taps. They were getting a lot of consumer complaints, so they wanted us to take a look at their water plant and their distribution network and see if we can optimize their treatment process and really clean up their distribution network. So this is the inside the water plant. They have two wells that come in. Their primary oxidant was just chlorine, and then they went through two contact chambers, which is these first two fiberglass cylinders, and then it went through two pressure filters. They used macrolide media to filter out the particulates, and then from there it was pumped down into the clear well underneath the water plant. So really, we did a three-step approach to this project, and the first step was really improve the treatment plants to improve their water quality standards. And the way we did that was we monitored the treatment plant over the summer and really just adjusted their chemical feeds, adjusted their process so that with the chemicals they were feeding, they were able to hopefully get iron and manganese below those secondary standards, so you weren't putting more iron or manganese into the distribution network. The second step of the approach was, once the water treatment plant was producing clean water with those standards, was to clean up the distribution network, because there's going to be a lot of buildup, there's going to be a lot of deposits, there's still going to be episodes of brown and black water even if you're putting out clean water for the next couple of years. So we developed a water model to flush the entire distribution system. What's really significant about it is the water model, we developed it so that we could simulate flows through hydrants and determine specific velocities through those mains to make sure it was getting a scour effect. And we did it in a systematic sequence so that it wasn't just being pushed around in the distribution system. Instead of flushing the hydrants, sometimes some cities can do that. So the third step was optimizing the treatment process, which we did from bench scale testing using a stronger oxidant that could remove the manganese when chlorine wasn't able to. So for the first approach, understanding the plant chemistry is important. Optimizing the plant to oxidize iron and manganese, and see if there's any limitations with their process if they aren't able to remove these constituents. So a little chlorine chemistry, chlorine or sodium hypochlorite. It dissociates in water and forms hypochlorous acid, which is a weak acid, and then it's free and available chlorine. The breakpoint chlorination curve is, I've seen it a couple times, but you feed chlorine and then a formation of chloramines, and then destruction of chloramines, and then you hit breakpoint, and then you start seeing free chlorine. We did some bench scale tests to see where the breakpoint was in the Sabin water plant, to see how much oxidant was needed for their system, see if they were overfeeding or underfeeding. the chlorine. A little bit about iron and manganese oxidation. Chlorine and potassium permanganate both form precipitates, the iron hydroxide and manganese dioxide. But understanding these formulas, and that, especially with potassium permanganate, if you feed too much potassium permanganate, more manganese can be put into the system. It's an important factor in those formulas too. Now, understanding the basic chemistry of the plant, looking at some limitations of their process that they had. One thing to note is that their 2 contact tanks that they had in their plant had pretty low contact time, which was only about 6.8 minutes or 7 minutes of contact time. Now, 7 minutes of contact time with chlorine can typically oxidize the majority of the iron in the water. But 7 minutes isn't really enough time to oxidize any manganese in the well water. So that was one limitation of the plant, was they didn't have a strong enough oxidant to remove the particulate in the filters. It wouldn't even form a particulate. So we first got out there, we took some samples of the distribution network and then the filtered water off of the macrolite pressure filters. The sample on the left is the distribution network sample. So you can tell it has a little brown water. It was off of the taps, it was off of somebody's house, and it has a little bit of iron color in it, but the water plant was producing clear water. So we knew there was a problem with the water plant, and then there were some particulates in the distribution network. When we first started data collecting in the beginning phase of this project, we noticed there was fluctuations with chlorine dose. We didn't know what to attribute that to, so we started taking a lot of samples, and this is the iron concentration in the clear well. And over a month, we noticed that there's at least one spike of pretty high iron content, and we realized that some of the injection ports were getting plugged, so sometimes that would go left unnoticed for a couple days, and a lot of iron and manganese would be pumped into the system. So over the course of the study, we found that there was a lot of these types of issues with the operation. So once we adjusted the chemical dose and really got the plant running smoothly to remove just the iron, it wouldn't remove or oxidize the manganese in the well water. We started noticing differences in the water plant. And this is a picture of the clear well. This is kind of when we first started. It has a hazy white color to it, which is iron precipitate. And this was after we optimized their system. You can see the ladder can go all the way to the bottom of that clear well. You can see that in the back. So now that the treatment plan was optimized with their current chemicals that they had there, they were producing good quality water, but not removing manganese yet. We wanted to develop a water model and develop the flushing plan to help clean up the distribution network. So we built a water model for the city of Sabin, and then developed a flushing plan to scour the pipe network in a systematic approach. So this is the water model. The color coding is the pipe velocities in the water main. So at this hydrant location, we simulate a 1,000 gallon per minute flow from that hydrant. And you can tell by the color, the blue is 6 feet per second, and then the light blue is 4, and the green is 2. So at this location, what we wanted was a 4 to 5 feet per second scour velocity, which would substantially clean the pipe networks. You can kind of cancel out the water mains that are in blue. or in that range. So we ran the model with all the hydrants, and we identified the least amount of locations that they had to flush to really clean out every single distribution network main in their system. This is a picture of the one of the flushing plans, and it'd be a little hard to see, but we developed 12 of them. We had to flush 12 hydrants for the city of Sabin, and this is the 1,000 gallon per minute flow. We kind of just gave them maps of 12 different flushing plans and how they can do it in a certain sequence. This is a picture of some water that came out of the hydrants before they were flushing. It was, that's some manganese and black water, and then this is after. We've done this for 2 summers now, and it's substantially cleaned up. Every spring cleanup, the clarity of their water has really improved from when we first started. Let me click this. And this is some of the iron and manganese that was It says it's not available, but it was just hydrant flowing, and you could see some really brown and black water from what they were doing. So the third approach to this project was to optimize the treatment process. They really wanted to be able to remove the manganese in the water and not a substantial cost to their system. So we performed bench scale studies using sodium permanganate, different doses, and we used a polymer to be able to capture these smaller particles, because it was forming, we found out as the sodium permanganate was forming smaller particles that the macrolide media wasn't able to capture. So in addition to sodium permanganate feed, we also had to add a polymer to the system. This is their raw water quality. Their iron was about 1.5, and they had a 0.5 milligram per liter of manganese. Their arsenic was around that 50 parts per billion, and about 2 milligrams per liter of organics, 7.5 pH. So this is a jar testing we conducted. You have your blank, and then you have different doses of sodium permanganate, potassium or sodium permanganate at 1 milligram per liter, 2 milligram per liter, and 3 milligram per liter. And if you ever dealt with permanganate, you know that when it turns pink, you've really overfed it. So what we're looking for is that brownish with a little pink tinge in the color, and not this full pink color. So we knew what the dose to start the optimization process was. And you can kind of see some iron particulate in the bottom of these jars. This is a pink jar that had quite a bit of potassium permanganate. So we found out we did a range dose of 0.4 to 2 milligrams per liter. And to really understand where you're at I call it the potassium permanganate curve, but there's a certain break point of where you get optimal feeding for that system. Because if you overfeed it, you're going to start seeing more manganese into the system, but if you underfeed it, you can also see more manganese. So you really have to do a wide range of doses to see where you get that optimal point for sodium or potassium permanganate. And one way to analyze that is to simulate the gravity filter with a 0.45 micron filter, and you can filter a sample that has been dosed with potassium permanganate through the filter, and then measure the concentration afterwards, and it will tell you if how much has been captured on that filter, how much will be captured in the media filter. So a couple of jar test results that we did. The first one we did was what's the demand in the system just using chlorine. So that breakpoint chlorination curve that I showed earlier, you'll feed the chlorine, and in forming chloramines you'll get destruction, and then right here is free chlorine. So it looks really similar to the breakpoint chlorination. So at breakpoint it took about 4 milligrams per liter of hypochlorite. Now we did some hypochlorite dosing to see if the iron and the manganese would get removed in the system, which is this graph right here. So the red is the manganese concentrations, and the blue is the iron concentrations. And then the bottom part of the graph is the dose. And so the iron starts out at about 1.2 milligrams per liter, goes down to 0.2, and iron after about 2 milligrams per liter is completely reduced and able to be removed. But manganese, even at very high chlorine doses, which is 5 milligrams per liter right here, you're still seeing 0.25, 0.3 milligrams per liter of manganese. So even at really high chlorine doses, we weren't able to see any oxidation of the manganese in the system. This is kind of the curve that I was talking about the optimal potassium permanganate dose. So again, the blue is the iron and the red is the manganese. Now the manganese levels right here at a 0 is about 0.4 milligrams per liter of manganese. And as you get down to this dosage of 2.5 to 3 to 4 to 5, you see the manganese concentration starting to increase. So we knew we had to rerun the test at a range of 0 to 2.5 to make sure that this 2.5 was optimal dosage for removing the manganese in the system. And as far as the iron, potassium permanganate is very, very quick acting, so right away the iron was completely oxidized in the system. We also did some arsenic testing on site. There's no easy way to test arsenic. You need a lab to do most of that testing, but we wanted to make sure that we were within the ranges of adding this new oxidant to the system, as it wasn't going to disrupt the co-precipitation of iron and arsenic. So this was a kind of quick test. It goes in the ranges of 0, 10, 30, 50 parts per billion. It's a color-coded test, and it was between that 0 and 10 range, so we didn't do too much further testing with that. So here's some recent plant filter tests off of the pressure filters. This is in 2012, and this is kind of where we started optimizing the plant. And this is the iron concentration versus time, and this is the secondary drinking water standard. And over several months, they've consistently been 0.05, 0.1 milligram per liter of iron. So they've really cleaned up their treatment plant as far as putting out more iron in the distribution network. And these are their manganese levels. So they're up in that 0.25 milligrams per liter. And then once we added the new chemical and started optimizing the plant, they're really, really close, and most of the time below the secondary standard of 0.05 milligrams per liter. So currently, after we've been doing that for several years, we're using an oxidant, a reox agent, to clean up the pipe walls or the biofilm or anything that's still attached to the pipe surfaces in the distribution network. So this summer, actually, we're going to be using that approach to hopefully finish up and clean the entire system. I'd like to thank the City of Sabin, operator support. They were really cooperative and really involved in the projects that we did as far as data sampling and getting us the stuff we needed. And also the environmental group and more engineering. So. Does anybody have any questions?
Yeah. So you have an arsenic treatment. First is just the filtration and then the arsenic treatment. Then all this chemical feed is after the arsenic treatment?
The arsenic test that I performed?
No, those tanks that you showed in the first picture.
Yeah.
So those are the tanks which have the arsenic media.
Yes.
So this chemical which you're feeding is after the downstream of the arsenic media?
No, but it's upstream of it.
Could you repeat it? Can't hear.
Oh, you're wondering if the sodium permanganate that we're feeding is upstream of the macrolide media or downstream?
Right.
It's upstream. It's injected ahead of the contact tanks so that they'll get proper mixing and then go through the pressure filters, and then they're able to be captured in the pressure filters. So the oxidant we changed it from chlorine to sodium permanganate, and we added a polymer upstream of the treatment process. And then it goes through the contact tanks and the pressure filters, and then it's filtered out in the macrolide media.
Any other questions? All right, let's give them a round of applause.